In this paper, we propose a novel algorithm for the design of high-performance coding schemes for fluorescence lifetime imaging. These coding schemes can achieve high signal-to-noise ratio and short acquisition times. First, we will briefly explain the fluorescence lifetime and its application. Fluorescence is the phenomena where a material absorbs light at certain wavelengths and then emits light at longer wavelengths. A widely used measure of fluorescence is the fluorescence spectrum, defined as the intensity variation over the wavelength. In addition to its spectral response, fluorescence also has useful transient phenomena. If a fluorescent material is illuminated with a short light pulse, the intensity of the emitted light decays exponentially over time as shown in the figure on the right. The rate of this exponential decay is called the fluorescence lifetime. The fluorescence lifetime provides important information about material properties which are often not available in the fluorescence spectrum. For example, the fluorescence lifetime can be used to distinguish between cancerous and non-cancerous tissue, sense surface pressure, perform fingerprint detection, and perform non-invasive artwork analysis. In frequency domain fluorescence lifetime imaging, the object of interest is illuminated with a light source that is temporally modulated by a modulation function. Then, the fluorescence emission from the object is correlated with a demodulation function at the sensor. The resulting image intensities are used to extract the fluorescence lifetime. The set of modulation and demodulation functions is called a coding scheme, and the image intensities are determined by the coding scheme. Our goal is to design high-performance coding schemes that can achieve high signal-to-noise ratio and short acquisition time given a fixed source power budget. Now, we will explain our approach. We derive a novel fluorescence lifetime precision metric based on a first-order differential analysis of the image formation model. Since this metric is extremely fast to compute and precise, it can be used to efficiently explore and optimize over the space of coding schemes. Please refer to the paper for a detailed explanation of the derived fluorescence lifetime precision metric. Using this novel fluorescence lifetime precision metric, we have been able to design a new coding scheme named expo-square that outperforms existing schemes such as sinusoid-sinusoid. Finally, we evaluate the performance of the proposed coding scheme in various scenarios through experiments. We also compared the performance of different coding schemes over full-frame fluorescence lifetime images. Since our hardware prototype is single-pixel based, a fluorescence lifetime image was created by moving the sample on translation stages. We made 6 solutions with different lifetimes by mixing 2 solutions in different proportions. This figure shows the fluorescence lifetime images of the 6 solutions obtained by the conventional coding scheme sinusoid-sinusoid and our coding scheme expo-square at a fixed acquisition time. Expo-square shows more uniform lifetime estimation results than sinusoid-sinusoid. This is more evident if we perform edge detection on the lifetime images for both schemes. For sinusoid-sinusoid, the spurious edges are detected within each individual sub-image. For expo-square, however, no edges are found except the boundaries between the solutions. This figure shows the lifetime images at low SNR of different fluorescent objects with 2 different lifetimes for the foreground and the background. The boundaries between the foreground and the background are nearly invisible with sinusoid-sinusoid, but clearly discernible with expo-square. This figure shows the results obtained with the conventional coding scheme and our coding scheme at different data acquisition times. Both coding schemes show better results with increased data acquisition time, but our coding scheme can achieve the desired SNR with lower acquisition time. In summary, we developed an algorithm for designing high-performance coding schemes in fluorescence lifetime imaging that can achieve high SNR and low data acquisition time. we demonstrated the advantages of the proposed schemes in a variety of imaging conditions using a modular hardware prototype that can implement various coding schemes.